So this is our project. It's a line following robot. We call it the third wheel because of the third wheel on the bottom. It makes it easier to pivot over everything because the way it turns is kind of like a tank, where it slows down each wheel to pivot around it. Powered off 4 AA batteries for 6 volts, and then using PWM control for each of the motors. The IR sensors, they're adjustable for whatever surface you have. It loses signal on the black tape, and that change of state is how we use that to guide the robot. It can make a fast or a slow correction or a hard correction, depending on how many sensors are actuated or not. A couple things about the code is that you hit the C button to start, you pick it up off the table, the motor stops turning, you put it on the table with no line, it moves slowly, and then you put it on the line and it goes full speed.
What was the hardest part about building this?
Really it was getting the PWM for the code, just because getting the different turning states right so it wouldn't just fly off the track.
So for my internship, we do a lot of forensics on swimming pools for lawsuits and other things, and most of the time they leak, and that's the problem. And a leaking swimming pool, it can be a $400,000 repair pretty quickly on just like a normal house. So instead of doing like a bucket test where you leave a bucket in there for 24 hours, come back the next day and see how much water has been lost between the pool and the bucket, I can get that information in about 10-20 minutes, because that encoder is sensitive to 2,000 counts per inch. So it'll tick every 2,000th of an inch.
As long as it's not raining.
It's hard to tell if it's leaking when it's raining.
So what we have is a fan mounted to a stepper motor, and then surrounded are aluminum plates. Each plate has a TC attached to it that's read from here to the microcontroller. We set a certain temperature, and if a plate goes above that temperature, the fan rotates to the specific plate and turns on to cool it off until it's below the temperature.
So it's turning, and then as soon as it reaches its destination, we'll turn the fan on.
This is Dr. Mason, which stands for Driving Robot Moves and Senses Obstacles Nearby. And it does that. It moves forward, and then if something's in front of it, it senses that and it turns. And if it gets too close, then it just stops.
Basically, it's got this thermocouple here. When you heat it up past the maximum temperature, the fan will kick on depending on what the temperature is at. The fan will spin faster or slower. All of the components are hot glued together on our nice solder board and covered up with this little Hummer. And so here's how it works. Go ahead and, right now the maximum is at 80, so once we heat this up, right now it's at about 40, the minimum's at 30, so it's spinning fairly slowly. We've got some little LEDs lighting up to see how much speed the fan actually has when it's at full speed. 7 of them are lit up. So now we're past 80 and the fan is at full speed for what we're going to run it at. The fan's all hot glued together, so if it goes much faster, it falls apart.
This is our project. It's a shooting range. So we wanted to develop targets that when they fell down, we shoot them with a Nerf gun, that they would pop back up using servo motors. We wanted it to do it autonomously, but we couldn't get the voids to all work together. So there's buttons on the microcontroller that'll raise and then catch the targets. And then in the back here, I don't know if you guys can all see them, but they're LED resistors. So they measure the resistance and then therefore the voltage when the targets are down. So it'll also keep track of score when the targets are down. Ready? Yep. Set, go.
wind tunnel, known as the wind funnel, because we put the fun in DAC. And so this is our wind tunnel. Basically, we with a potentiometer we can control the wind speed coming through the tunnel, and then the whole genesis or the purpose of this is to compare blade designs between on our motor. We have a DC motor that gives us some voltage feedback, and that'll tell us how fast it's spinning. And then on our LCD we have a calibrated fan blade that'll give us basically 100% at max speed, and then every fan blade that we test before or after that is, if it's over 100, that means it's a better fan blade. If it's under 100, it's a worse fan blade. There we go. And then once that's assembled, you can put this all back.
Okay. You want to bend it down and get it here.
There we go. And then we can turn our fan back on. And voila, we have motion. And then we have our LEDs assigned so that max power, we have all 7 LEDs lit up. Minimum power, we'll have less LEDs lit up. And then the green just tells you if it's on or off. And then we also can collect different sets of data, so if you want to compare the different fan blades.
Sonar sensor, it's almost like a homemade radar gun, but we use sonar instead. So we actually have a live feed display of the distance, and it tells you also how fast you're going. The further you go away, the more LEDs that will light up, so you can also see how far you're going.
We decided to make a toaster that has a 14-segment display, so you can choose any of the 26 characters of the alphabet or any of the numbers and toast that into your bread. So there's 14-segment display, but instead of LEDs, we have resistive wire that heats up, and it takes about 5 amps to heat up one wire. And so we're switching between all these relays that needed to be rated for 5 amps. On here, we actually have a countdown so I can keep you updated. It says printing toast. It told me which letter I'm printing, which is an M for Mason. And then there's also a time. We're currently at 443 seconds and counting. So it's going to be a couple minutes. MTV, we're back with my toaster. We've got about 7 seconds left before we get to see the final product. It actually just gave me the sign that says toast complete, enjoy, which I intend to do.
Ah.